If you're ready, we can start.
Yeah,
So,
right.
It's a pleasure. Welcome, everyone. It's a pleasure to have here on the big screen, Sukanya Chakrabarti. I hope I said it well. From the University of Alabama. She's professor there, and before she was an Einstein Fellow in Princeton, I think. And she's working in, I look to the CV and the impressive number of topics that involves basically everything that is time domain, multi-messenger astronomy, try to apply different techniques that apply in different fields of astronomy, including study of planets, to actually understand the dark matter and a lot of the things. And is also working on galactic dynamics and radiation transport. So, and today she will talk about, she changed slightly the talk from the previous idea, and is talking about the constraint on the, towards the precision measurement of dark matter through, it was still with Pulsar Timing array, or including that?
Yeah, I'll talk about those areas. Yep.
Among different things. Okay, the stage is yours. Thank you very much.
Great. Thanks so much, Emma, and thanks for the invitation. So I think you can all see my screen.
Mm-hmm.
Great. Okay, so I'm going to talk with you today about techniques that we've developed that now enable us to directly measure the very small accelerations of stars that live within the gravitational potential of the Milky Way. So this is at the level of about 10 centimeter per second per decade, which is a very, very small change in the velocity over a decade baseline. But due to advances in technology, we can now directly measure this change. And these direct measurements of accelerations of stars in the Milky Way give us the most precise probe of the mass distribution in the galaxy, both the stars and this elusive dark matter that we've been trying to understand for a very long time now. So I'll talk about several techniques that we've developed, and I've been fortunate to have done this work with some fantastic collaborators and students, and my students are in the asterisks here. So let me begin by motivating this, by contrasting it with what's been done in the galactic dynamics community traditionally. So traditionally, what you do in galactic dynamics when you're trying to infer the galactic potential that includes the distribution of dark matter in the Milky Way is you model a snapshot of the positions and speeds of stars, a snapshot in time. You model a snapshot in time under a number of simplifying assumptions to estimate an acceleration, okay? The key simplifying assumption there that is made traditionally in galactic dynamics is the assumption of equilibrium. Now, a number of people, ourselves and others, have shown that the true acceleration, when you have a time-dependent potential, okay, like you have for the Milky Way that's due to interactions with dwarf galaxies, okay, when you have a time-dependent potential, when you have an interacting galaxy, the true acceleration is in fact different than what you get if you estimate accelerations using this, what is known as kinematic analysis, where you're modeling a snapshot of the positions and speeds of stars in the Milky Way to estimate an acceleration. And there are a number of lines of evidence that now indicate that the Milky Way has had a highly dynamic history. Let me go through a few of those with you. This is from analysis of SDSS data that shows these vertical waves in the disk of the Milky Way that were produced as a dwarf galaxy came by and perturbed the disk, leading to an asymmetry in the north-south star counts in the galactic disk. Now, prior to my work on these extreme precision time series measurements of accelerations, I spent a long time working on simulations of the Milky Way interacting with dwarf galaxies, and I'll show you some of these. This is a simulation of the Milky Way interacting with the recently discovered dwarf galaxy, Antlia 2, discovered from analysis of Gaia data. And this is the stellar response. So you see the dwarf galaxy come by and disturbing the Milky Way, and you see the tidal streams that are forming. And this is the gas response. And together with my students, we've also looked at the formation of the Magellanic Stream due to both ram pressure stripping and tidal effects. Now, the one constant across these simulations and many others that we've done now over the past decade is that the galaxy is changing. And due to advances in technology, we can now directly measure that disequilibrium. And we've now developed 3 different techniques through which we can do this. And we have several observing campaigns underway to use these extreme precision time series observations to measure accelerations directly. And I'll go through these with you. And by the way, please feel free to ask questions both during my talk and after my talk. I'm very happy to take questions anytime. So this is a big group of people who've been working on this, and it's a very interdisciplinary group that includes folks from the exoplanet community, from transit timing, and from people who are working on analysis of compact objects. Now, I want to contrast this, what we're trying to do to measure these tiny accelerations, with a successful acceleration measurement, a very well-known acceleration measurement. This is the measurement of accelerations of stars near the galactic center that led to a quantitative determination of the mass of the supermassive black hole at the center of our galaxy. And in this movie, you can see the orbits that are traced out. And these orbits are determined from these measured accelerations. Now, these accelerations are much, much bigger than the accelerations that we're going after, okay? So these, you know, in our community today, we can now fairly commonly measure these type of big accelerations. So for reference, this is about 0.3 centimeter per second squared. Okay, the accelerations of stars near the galactic center. And what we're trying to go after is about 3×10⁻⁸ centimeter per second squared. So there's a big difference, but we can certainly measure big accelerations and have been able to for some time. The work that was shown here by Andre Ghez and others was conducted over a 20-year baseline. Now, the other example where this is now done very commonly is to use RV measurements to characterize black holes around luminous companions. And again, I'd like you to note the scale here. You see the radial velocities changing at the level of tens of kilometers per second, okay? And yet, you know, in our case, we're talking about much, much smaller changes, okay? So that's the key difference in the work that's been done before in acceleration measurements by the astronomy community and what we're going after. So certainly in this latter category, in characterizing non-interacting black holes, there's been quite a bit of progress. We ourselves have also worked on this and characterizing non-interacting black holes from Gaia DR3. This is the discovery of the first approximately 10 solar mass black hole around a sun-like star, identified from DR3 and with follow-up spectroscopy. Both of these papers were essentially contemporaneous. They came out last year. And again, you'll note that these radial velocity changes are, of course, very, very large, okay? This is something that is now really I would say not necessarily easily done, but it is very straightforward, and many groups are involved in this. So progressing now to what I like to call real-time dynamics. So we talked about the acceleration measurements of stars near the galactic center. That's a big acceleration compared to the ones that we're after, okay? So the stars near the galactic center experience an acceleration of about 0.3 centimeter per second squared, okay? We're effectively trying to measure about 10 centimeter per second over a decade baseline, okay? In the same units as what I just quoted, that's about 3×10⁻⁸ in units of centimeter per second squared. And so we need really, in order to measure these accelerations, these very small accelerations, we need extreme precision radial velocity observations using the most precise spectrographs. The one that we've been using is Espresso on the VLT over the last couple of years. I'll talk about that in a moment. I'll talk to you about some of our simulations of the Milky Way interacting with dwarf galaxies to contrast the expectations for a static acceleration profile with an interacting acceleration profile. And I'll review the first measurement of direct accelerations, which was possible from analysis of compiled pulsar timing data, which has been ongoing now for a few decades. And from analysis of these pulsar timing observations, in particular, what we use is the time rate of change of the binary period for binary pulsars. We were able to determine for the first time a couple of years ago the midplane density, the local dark matter density, and the shape of the galactic potential. And finally, the most recent technique that we developed, the idea is similar to pulsar timing. You're looking at essentially a periodic signal, okay? You're looking at eclipsing binary stars that have been measured very precisely by Kepler about a decade ago. In this particular case, you're looking at eclipses. If you have a very high signal to noise eclipse, you can pinpoint the midpoint of that eclipse very precisely. Now, these eclipsing binaries, like the other stars, they live in the galactic potential of the Milky Way. And the midpoint, just due to the fact they live in the potential of the galaxy, is going to shift, okay, about 1/10 of a second over a decade baseline. And that is now possible to measure today with HST or JWST. Now, these may seem like fairly disparate techniques, but the one thing they do have in common is their effective precision, which is about a part in a billion. Now you can express, we're talking about accelerations, which you can express as a change in the frequency, which is basically corresponds to the vibrato, okay? That very small change, the vibrato of an opera singer. That's essentially what we're talking about. And that's something that you can hear with your ear. And due to advances in technology, we've now gone to the point today that we can measure these very small accelerations. Now, what we've essentially been doing is we've been adapting techniques from two areas in astronomy that have seen significant advances in precision measurements. And these two areas are in the hunt for exoplanets and in tests of the theory of general relativity. So I'll first talk about the extreme precision RV measurements. So as you have a planet that's going around the star of course pulls on the planet, but the planet also tugs on the star, leading to these very small shifts in the spectral lines that we can now measure with improving precision. And you'll see here this plot on the left, which shows the radial velocity precision as a function of the commissioning year of the telescope. So there have been, as you can see, there have been significant improvements in precision here, and where we are today, the instrument we are using is Espresso on the VLT, which has gotten to, in some cases, on the level of about 30 centimeter per second radial velocity precision. And the instruments that are expected to be available on the ELTs should achieve comparable, if not better, RV precision. The primary difference will be that they will be on much larger telescopes. And so the goal then is really that I think can be achieved is one can get direct acceleration measurements across the galaxy and not be limited to small volume as we are today. So now, we're getting these acceleration measurements, and given an acceleration measurement, we directly get the potential. Given the Poisson equation, we can then get the total midplane density, which is known as the Oort limit. And if you subtract out the baryon density, you can get the local dark matter density. So this is a very straightforward approach in our case. Now, this is a century of compilations of the local dark matter density from kinematic analysis. Okay, that is the method where you assume equilibrium and you estimate an acceleration from a snapshot of the phase space density of the positions and speeds of stars. And I'll show you our value superimposed on this a little bit later. So this is something that's important for interpreting direct detection experiments for dark matter, because the recoil rate per unit energy per unit mass is proportional to this local dark matter density. So let's start by looking at some baseline expectations, okay, for the static potentials. Okay, this is a potentials that are not changing as a function of time. We're looking at the on the y-axis here is the change in the line of sight velocity over a 10-year baseline, okay, as a function of height above and below the midplane. So a few different static potentials are shown here. Some of these are commonly used in the literature, and I've also shown in these red dots an isolated spiral galaxy simulation. So what I'd like you to notice is that the overall scale here for the acceleration is about several centimeter per second change over a decade. And they're all fairly symmetric on either side. These acceleration profiles are pretty symmetric on either side of the midplane. And we're now going to contrast this with interacting galaxy simulations. So just a little bit of background on the kind of simulations that we'll be looking at. So this dwarf galaxy, Antlia 2, that was discovered from analysis of Gaia data, was dubbed the hidden giant. Okay, it's you can see it here in this press release image. It's about as big as the LMC, but about 4,000 times fainter. It's pretty close to the plane of the galaxy, and it's about 130 kiloparsec away. We have proper motions, so we can calculate for an assumed galactic potential. We can calculate the orbital distribution of Antlia 2 within the galaxy, assuming the initial conditions that we have from the proper motions from Gaia. So that's what's shown here in this topmost figure. This is showing the distribution of pericenter values. And the average pericenter in this case is about 15 kiloparsecs. So there are some, fairly close approaches that lead to this kind of interaction that you saw earlier that would lead to significant perturbation on the galactic disk. And this is the stellar disk, as it turns out. This leads to essentially a near coplanar orbit, which would explain these large perturbations that are seen in the outer gas disk of the galaxy, these large spiral perturbations in the plane in the outer part of our galaxy. So we, quite a long time ago now, we made a prediction for the dwarf galaxy and the necessary parameters the dwarf galaxy would have to explain these disturbances. And it turns out that both the radial location of Anthea 2 and the nature of the orbit do match the predictions, our earlier predictions. So let's now look at these acceleration profiles. Okay, so both of these plots are showing acceleration profiles from these from two interacting simulations. The top is the Milky Way interacting with Anthea 2, and the bottom is the Milky Way interacting with the Sag dwarf. The blue dash line here is the equilibrium initial condition. Okay, and the green line is the post-interaction profile. This is the acceleration profile after the dwarf galaxy has interacted with the simulated Milky Way. And you'll notice that the equilibrium initial condition acceleration profile is symmetric on both sides of the midplane, just like for the static potentials. But the post-interaction profile is clearly asymmetric. Okay, so this is the kind of difference that we can expect to see in our direct acceleration measurements in our time series extreme precision observing campaigns that we have underway. And some of these differences can be significant. So the first survey that we began was our extreme precision radial velocity survey with Espresso on the VLT, where we're trying to measure using radial velocity line of sight observations. We're trying to measure the changes in the radial velocity, the very, very small change in the radial velocity that is induced by the galactic potential. This is at the level of the 10 centimeter per second per decade number that I mentioned. So this is a very small acceleration that we're trying to measure, right? And in this case, as well as in the other techniques, we have to think very carefully about contaminants to the galactic signal. Okay, so these can include external contaminants like planets, stellar binaries, as well as internal contaminants. Okay, that is, stellar jitter that's due to internal processes like convective instabilities, or that can be magnetically driven, that confounds the signal that we are trying to measure. Now, these stars, they tend to, the brighter they get, they tend to be more noisy. So we have chosen subgiants as a compromise between the brighter stars that would allow us to trace the galactic potential further out, and the very faint stars that live at the jitter minimum. So let me also go through the our analysis of the external contaminants as well. So, this was done initially by, I did a population synthesis model where I'm sampling from the demographics of planets around subgiant stars. Okay, so this is sampling from the demographics of planets around subgiant stars, or this is correct to the extent that our knowledge is accurate in this regard, but the result is fairly clear. So the binaries are shown here in the green, and you can see the binaries would lead to a very large change in the RV. And so we can easily throw them out. In fact, we have already thrown them out. It's very clear in the espresso spectra. The planets are shown in the red, and the single stars that faithfully trace the galactic signal are shown in the blue. So there's some overlap with the planets, particularly the low mass, long period planets are something of a contaminant, but they're not a very large, they don't present a very large contribution. And statistically, we were able to show that you can reject the null hypothesis that the signal is due to stars with planets at high confidence.
Right.
So,
can I ask a question now? Yes, you're rejecting the binaries with very large amplitudes, and you're dealing with stars that have planets that give small amplitudes. I would think that if you have large amplitudes, they are easy to take out of the data, and if they're binaries, they're less likely to be contaminated by planets. So there might be better candidates than single stars in terms of isolating the small RV variations. So there must be something wrong with my argument if you're rejecting those.
Okay, so this is the idea here is that this is a initial, let's say, sort of quality assessment we did to see if you have a sample of 70 stars, okay, some fraction of them were in binaries. And again, the binaries are also being sampled from a population that are expected, have orbital properties that are typical of subgiant stars. And that is the case for the planets as well. So this is the modeling is subject to our knowledge of planetary systems and binary systems for subgiant stars. And this is just an expectation at the moment to see, can we expect to get a result that might allow us to extract the galactic signal from stars that are not significantly contaminated by planets or binaries. Now, there may be binaries that lead to low amplitude changes that are not included in the typical demographics that we know about, and would therefore not be modeled here. In principle, you could remove those too. You would just have to model their orbits and so forth and remove them. But that's not what was done here in this initial study.
Thank you.
So now, this is this 10 centimeter per second is basically the speed of a crawling baby, and not very fast baby at that. And we're having to also contend with bunnies and things like that. So now, I think there are many surveys now that have successfully looked at, have tried to identify binaries. And we also, I should have said, we did cross-check with Apogee, and we removed anything that was identified as a binary, and we can do that ourselves in the data that we continue to get. So I think for large external contaminants, I think we've been able to do pretty well. As the question asked, it may be that the smaller amplitude contaminants still need more work, and that will become more clear as the survey progresses. But one thing that we do have to worry about, because we want to get to this 10 centimeter per second, is this stellar jitter, this internal contaminant that we have to contend with in really all stars. And our selection was done with this in mind as well. So what's shown here is the error in the RV slope as a function of the number of independent measurements. Now, the the slope of the RV curve is the acceleration, right? And the error in the RV slope is how precisely can you measure the acceleration. This is shown here specifically for standard RV stars for the LCS high-res survey that was conducted over 10 years. Now, this is not high resolution for us, but it nevertheless gives us maybe some guidance for what we can expect. The resolution here, I think, was about several meters per second. So the dashed line here is 1/√n. Okay, so you can see that the error in the RV slope does approximately follow that, approximately follow the 1/√n. It's approximately Gaussian. And so if we are lucky and if we're able to select the low jitter stars that live at, say, a jitter minimum of 50 centimeters per second over a 10-year observing survey with 25 independent measurements, we may be able to get to our goal of 10 centimeters per second. So these are, some of the kind of spectra that we're looking at. You can see in some cases, you can see the double peaked cross correlation. You see the binary separating out. There's some that have a little bit of extra flux in the calcium line cores. We don't want those. We want the ones that have essentially no flux there. These are the basically very low magnetic fields, low rotators. These are the quietest stars that we've selected for our survey. Okay, so, and the baseline has been established now with the espresso observations, and we're basically going to continue monitoring for the next several years. We should be able to release upper limits in a few years. Okay, I'm going to move on now to our recent work on pulsar timing. From which we were able to measure the galactic acceleration for the first time. This is now actually a couple years old, actually, so maybe not so recent anymore. So pulsars are fantastic clocks, right? They're temporal stability rivals, atomic clocks. There's talk of using them to form a galactic GPS system. This is a slow pulsar. Pulse profile is at the bottom. Now, the ones that we use, the ones that have been timed most precisely, are these millisecond pulsars that spin hundreds of times per second. And by looking at pairs of pulsars, okay, by looking at pairs of binary millisecond pulsars, and specifically looking at the change in the orbital period, we can use them as galactic accelerometers. So let me go through that with you. So this is the distribution of the binary millisecond pulsars. We had a grand total of 14. They're fairly local to the sun. They're all within about a couple of kiloparsec of the sun in vertical distance and galactocentric radius. And here in our press release image, you can see the Sagittarius tidal debris and other aspects of the galaxy showing that it's highly perturbed. So here's the setup here. The quantity that you observe, the observed quantity, is the time rate of change of the binary period. That's on the left-hand side. On the right-hand side are the physical mechanisms that lead to that change. Okay, one is the fact that these pulsars live in the galactic potential of the galaxy. There's also this so-called Shklovsky effect that's due to the apparent orbital change due to the pulsar's transverse motion, and you can calculate that. If you know the proper motion mu and the distance d, and we have these measurements from pulsar timing for these specific systems. And these are compact objects on tight orbits. Okay, so there can be gravitational radiation emission. So you also have to worry about this general relativistic effect. Now that term also can be calculated if you know the masses and the eccentricities, which we do for these systems. So, basically we know everything on the right-hand side, except for this pb.gal term, okay? So we can solve for it, and given this, we can calculate the acceleration directly from time series measurements. We've excluded sources that are in globular clusters, because in those cases, the globular cluster potential dominates, and we are restricting ourselves to pulsars that have both proper motion and parallax measurements from pulsar timing. So this shows the distribution for the pulsars as a function of galactocentric radius and vertical height. And you can see that the measurements are at the moment fairly local. And I'll go through a simple example with you. This is just meant to be illustrative. It's not meant to be comprehensive. Okay, so let's write the galactic potential like this. Let's say that it's separable in R and Z. And we'll write the radial component in this way, where beta is the slope of the rotation curve, and VLSR is the local standard of rest velocity. And again, continuing to be very simple, we'll write the vertical component like this, where alpha-1 is the square of the frequency of low amplitude vertical oscillations. And now we simply use the Poisson equation, okay? Because we're measuring acceleration, so we can directly get the density here. And for the specific case, beta equals 0, okay, flat rotation curve, we have that alpha-1 is very simply related to the midplane density, which is known as the Orth limit in galactic dynamics. So this is our from our MCMC calculations, is the posterior distribution for this parameter, which is essentially the Orth limit. You can see that it's tightly constrained from the pulsar timing measurements, and the value is there. Now, given the extent of the pulsars, our stronger constraints are in the vertical direction. So we were basically able to constrain the vertical component of the potential, but the radial component was not as well constrained. So you can see here, beta, the slope of the rotation curve, is was not at that time very well constrained. So if you subtract out various measures of the baryon density, you can get a measure for the local dark matter density, and there's our value superimposed on the century of kinematic measurements. And you can see that we are somewhat on the low side. The uncertainties on this are large because this is a much smaller number. So to measure it at more confidently, we'll have to improve our uncertainties on the Orth limit. So we were also able to get a constraint on the shape of the potential as traced by the pulsars, and this essentially corresponds to a very disk-like structure. So this is comparing this figure on the top left here is comparing the accelerations, the observed line of sight accelerations, to various models, the kind of models that I talked to you about earlier, that are commonly used in literature. These are static potentials, and this comparison is now on a per pulsar basis for the 14 different pulsars we looked at 2 years ago. And you can see that there's some differences, okay? The differences are at the level of a factor of 2, which may arise from out of equilibrium effects or deviations from symmetry, and some of our students are looking into that now. Now, we were not able to, one of my goals was to see if we could directly look at the effects of galactic interactions or substructure in the pulsar timing observations. We were not able to do that in the initial study, but maybe this is a way forward. So what's shown here in this figure in the bottom is the derivative of the vertical acceleration, and as a function of height above and below the midplane. And our values are shown in the gray, with the various static potentials in the simulations shown here in the colored dots. And you can see that if we'd been able to go out even a kiloparsec on either side, we might have been able to see these deviations due to time-dependent effects in the simulations if we'd had even a slightly larger dynamic range. So, basically what we've been able to do thus far is constrain the smooth component of the potential, which is, a significant step forward. But what we're really after is, with these acceleration measurements, we want to understand what is the nature of dark matter. So you can see here from this review paper, 3 depictions of different models of dark matter that have fairly different distributions on subgalactic scales. So what we're really after in constructing these different surveys with these different techniques is we want to see if we can measure the effect of the substructure in the acceleration profile directly. In the Pulsar timing language, this would correspond to measuring jerks in the acceleration field. That is not just the first derivative, but the second derivative. Okay, so this is an example of not smooth accelerations, but non-smooth accelerations. Okay, this is George Costanza navigating New York City traffic. In our case, of course, we're trying to navigate the non-smooth accelerations we're after is due to the substructure of dark matter that we're trying to measure with our pulsar sample. The earlier pulsar sample is shown here in the blue, and this is our espresso sample here, for which we started to get espresso observations about 2 years ago. And we're going to continue monitoring for we hope for the next 8 years, which should enable us to get the EPRB measurement as well. So you can see the espresso sample is designed to be different from the pulsar sample. It's designed to probe this fairly small range of radii, but to have a much denser sampling in this region, with the goal of seeing if we can directly measure these non-smooth or these jerks in the acceleration. So finally, moving on to our last technique here, which is using eclipsing binary stars that produce these very, very deep, we're interested in sources that produce very deep eclipses. So, these stars also live in the gravitational potential of the galaxy. And if you have a very high signal to noise light curve, you can pinpoint this midpoint of the eclipse very precisely. And if you were to be able to do that over a decade, you would see that the midpoint is going to shift by about 1/10 of a second. Okay, so over this time baseline capital T, which is a decade, this eclipse midpoint would shift by about 1/10 of a second due to the galactic potential alone. Now, to measure such small shift requires very high photometric precision. This is something that is imminently possible to do because in all of these techniques, what we basically have to do, like with espresso, what we did is we established the baseline very precisely, and now we're at a stage where we can start to measure changes relative to that baseline. The same is true for pulsar timing. And in this case, we have a big advantage because Kepler established the baseline very precisely a decade ago for a large sample of eclipsing binary stars. And now with space-based observations, we should be able to measure that shift due to the galactic potential. However, like all of our techniques and observations, we have to worry about contaminants to this very small signal. Okay, there's of course, the shift due to the galactic potential, but we, for eclipsing binaries, we may have to worry about tidal decay, the precession, the GR precession due to an eccentric orbit, tidally and rotationally induced quadrupole moments. So we have to calculate all of these dynamical effects and ensure that the shift due to these other physical mechanisms doesn't overwhelm the small signal that we're trying to measure. So the shift in the eclipse midpoint time is shown here for the ith dynamical effect, color-coded here, as a function of the binary period for these different physical mechanisms. They all produce a shift, and we can now populate this plot with real sources because work that was done by Eric Egal and others in his group analyzed the Kepler light curves to calculate the stellar and binary parameters. Okay, so we can basically calculate all of these physical effects and put about 700 EBs on this kind of plot. Okay, so the solid green line here is the galactic signal, this shift at 1/10 of a second, and these other dynamical effects are also shown here. So you can see that, in fact, there are quite a few sources, about 200 sources that fall below the green line, for which all other dynamical effects are subdominant to the galactic signal, such that if we were to get HST or JWST observations today, we could measure that shift directly with a large enough sample. We should be able to characterize dark matter substructure in the Milky Way. And similarly, as before, we have some expectations. These are just theoretical expectations for external contaminants due to planets, and we find for circumbinary planets, this is not expected to be large. And so given a light curve, particularly given the photometric precision and the depth of the eclipse, you can determine the precision on the eclipse midpoint time. And there are a large number of sources from the sample that have a good enough precision such that we should be able to isolate the galactic signal. So this is what the eclipses look like. This is a simulated HST light curve. They're fairly deep eclipses. Timing precision posterior is shown here on the right. For these sources, we basically need HST or JWST level photometric precision to get to the timing precision that we need to measure this very small shift. So this 1/10 of a second, by the way, is comparable to the reaction time of the world's most elite athletes. And as you know, I'm coming from Alabama, and we've got a pretty good football team here with football players with this level of 1/10 of a second reaction time. All right, so in the remaining time, I'll just talk a little bit about some work that my student has done in developing a model that incorporates both the direct acceleration measurements as well as kinematic methods to ultimately produce acceleration measurements across the galaxy. And this is inspired by the distance ladder, right, where we're calibrating indirect measures of the distance, let's say from Cepheids, to the most direct geometric measure of the distance, the parallax. Okay, so similarly, we can calibrate indirect measures of the acceleration, let's say from stellar streams that cover a wide range, a very large portion of the galaxy. You see streams going out to 100 kpc and beyond in the Milky Way and in external galaxies. So we can calibrate the accelerations from stellar streams that are used, these indirect accelerations, to the direct acceleration measurements from pulsar timing. And of course, with Rubin and Roman, we expected to discover many more stellar streams in the galaxy and beyond. So this is a means of trying to go beyond the fairly local measurements that we have at the moment. So the idea here is, given the measurements, we can look at clustering in action space for the streams. And the streams will tend to be more clustered in the correct potential. Okay, so you can see here in the best fit potential, the streams are more clustered than in a potential that is 1 sigma away from the best fit potential. So that is how we determine the best fit potential from stellar streams. So we looked at, my student looked at a set of streams here, some of which overlap with the pulsar, some of which go further out in the galaxy. And the goal here is to get joint constraints from stellar streams and pulsar timing. And given the clustering and action space and a statistical method that we use to determine the best fit potential, we get the potential from stellar streams, and we can then determine joint constraints for both of these techniques, from direct acceleration measurements and from the streams. Now, one interesting result here is that now the acceleration is shown here as a function of height from the pulsars and for the individual streams, as well as a sort of combined measurement from the streams. The streams tend to lead to much shallower values for the accelerations, as you can see, relative to the direct acceleration measurements. Now, this may be because the streams are are not as influenced by the local measurements, or because the choice of potential does not prefer disk-like potential, and that's something that we're looking into at the moment. But our paper gives a fitting relation that can be used to correct for the acceleration inferred from stellar streams. Okay, so let me go ahead and summarize. So we've been trying to develop techniques to carry out time series extreme precision observations of the accelerations of stars that live within the gravitational potential of the Milky Way, which gives us the most direct handle on dark matter in the galaxy. We were able to determine fundamental galactic parameters from pulsar timing for the first time a couple of years ago. And we found values for the mid-plane density and local dark matter density that are close to but lower than modern estimates. The shape of the galactic potential traced by the pulsars is close to that of a disk rather than a halo. In this initial study, there were large uncertainties in the slope of the rotation curve, but those should improve soon with future data releases. I think, the combination of these various different techniques, that is probably what holds the most promise for producing constraints on substructure in the galaxy. And my goal, with these various surveys, particularly with our EPRV survey, is that, my goal is that I hope that it will serve as a pathfinder for the ELTs, which when they come online, will be able to carry out direct acceleration measurements across the galaxy and potentially even beyond. And I will end here, and I'd love to take more questions. Thank you so much.
So very nice talk. I really don't work on anything related, but so it's probably a very naive question. There was, I suspect there's an intrinsic astrophysical limitation in the measurement of all this acceleration. That is, for instance, the presence of the stochastic gravitational wave background that will alter your measurement of either periods or velocities and acceleration. But I really don't know if that's really a concern, or we're talking about scales that are much different. So you never mention it, so probably there's a very good reason for that. Can you comment on that?
Yeah, so that may be a contaminant. It's something I think we need to look into more in more detail, the nanograv measurement, as you know, of the gravitational wave background was done only fairly recently. It was possible to get to the precision that was needed to measure that particular effect, which arises due to the correlation in angular space. We are looking at specifically at accelerations at XYZ positions, not a correlation in angular space. And the signal is of a larger magnitude as well. But nevertheless, there may be some contamination at a lower level. And it's something that we maybe need to look into as well.
Thanks.
There is time for one last question.
Thank you for that great presentation. I see why you got all that VLT time. And I'm sorry if my question is not really related with the core of what you're presenting, but you started with presenting a binary system with a 10 solar mass black hole and a 0.9 solar mass main sequence star. Was there any work from your team to explain how you end up with a system like that, coming from the stellar evolution scenario?
Oh, yeah. So I didn't really talk a lot about that. This is work that we did last year as the DR3 data was released, and it was clear, well, various people were working on it, as you might know. It was clear from an initial look at the binary catalog that there were some interesting sources given the mass ratios. We were focusing on large mass ratios, and then we started to get follow-up spectroscopy for sources that looked interesting from that angle and from the analysis of the spectral energy distributions. That is, it looked like there wouldn't, that the SED could be explained by the single star alone. Now, we were not able to give, I would say, an entirely satisfactory explanation for how this kind of a system could come to be. We speculated that maybe it could be a triple, and maybe future observations could detect that. Maybe there's a source that's in the sort of mass gap region that we didn't see. But, with RV observations that cover a few months, it just wasn't possible to give definitive constraints, but we have some speculative discussion in that paper.
Thank you.
Okay, let's thank our speaker again.
Thank you very much.
Have a good day.
Okay, bye-bye.
Bye.